Now I'm going to talk about carriers generated during non-equilibrium conditions. Basically, at thermal equilibrium, everything stays the same. We talked about that. At one temperature, with no voltage applied, you can figure out the number of carriers and you're done, and you know how many there are. If you multiply the two numbers together, the number of holes and the number of electrons, you get the intrinsic number squared. It's all balanced. So if you can find out the number of holes and you know the intrinsic value, you can calculate the number of electrons, or vice versa. If you change the conditions so you're not in equilibrium, then something will happen. You will start to get charge carriers. But it will take time to get to the next state of equilibrium. So if you say increase the temperature and you've got more heat, you're going to have more carriers that are produced, and if the temperature goes up and then it stops, eventually a new equilibrium condition will be reached. But in the meantime, there's like this weird non-equilibrium state, and some really strange things happen. So first of all, there are two things that are going to happen. Excuse me. Oh, that's so much better. Now I can talk. There are two things that are going to happen. There's going to be carrier generation and carrier recombination. Generation is when electrons move up to the conduction band. Recombination is when electrons go back down and recombine. Both of these things are happening all the time. They don't stop because of thermal equilibrium. But in thermal equilibrium, the generation rate of holes, the generation rate of electrons, the recombination of electrons, and the recombination of holes is all the same. So the number that are being created and the number being destroyed are the same when you're at equilibrium. That's why when you calculate the number of electrons and holes, it stays the same. They're not always the same electrons and holes, but the actual net number stays the same. If you get excess carriers, and these are ones that are basically created if you increase temperature or do something like that, they're created in pairs. So remember, like if you dope something, you get more electrons than holes. But if you're in non-equilibrium condition, you get more electrons and holes. And they get created in pairs just like in intrinsic material when you get electrons and holes created in pairs. So they're created by an electron moving to the conduction band and leaving behind a hole. So you'll get more electrons and you'll get more holes. This is where it gets just weird for a minute, but don't worry about it. Basically, when you create new ones, you're adding those to the original ones. So you calculate the number of electrons and the number of holes. That's N0 and P0. Then there's added this delta N and delta P, which are the excess ones, which would be equal in numbers. Even though the NO and PO might be unequal, the delta N and delta P would be equal because they're getting created in pairs. But what this means is because of this, I'll tell you in a minute, but basically if you make extra electrons, so say there's a photon that comes in, and that's what that just was. Photon comes in and you create extra holes and extra electrons because that's extra energy. So it could be heat, could be light. You'll notice that the number of electrons in this material is greater than the number of holes originally. So what kind of material was that? N-type, yes, because there were more electrons than holes. But when you get the total number of electrons and the total number of holes, you can't multiply them together to get the intrinsic concentration under these conditions. Because you had your numbers that balanced, then you added on equal numbers to each one, so you can't multiply them together and get the same value. What will happen eventually is when it equals out, then that will happen again. So once everything settles down into a new equilibrium, then you can multiply the number of electrons and holes together and get the intrinsic number squared. But during this transition time, you can't. Recombinations are going to also happen all the time. There will be electrons in the conduction band that fall down into the valence band and recombine. And the recombinations also occur in pairs because whatever recombines, electron eliminates a hole, we get a nothing, and the rate at which they recombine is the same. This is why this is kind of simple. So again, when they recombine in pairs, they emit something. And this goes by a little fast, but when those disappear, something comes out, some kind of energy is released. With gallium arsenide, it's a photon, which is really, really useful because that's how we get light-emitting diodes. With silicon, it's something called a phonon, which is a quantum of energy that comes from lattice vibrations. It's not anything you can see. Something I never heard of until I started teaching this class, but they do exist. It's just a quantum of energy, but it's not a visible quantum of energy. So it is quantized, but not quantized in a way that we think of like light or something like that. So it's not really a useful form of energy. So can we figure out mathematically how many excess carriers there are? Do we really want to? Maybe, maybe not. We're going to make it easy. So what we're going to do is we're going to think about how many excess carriers there may be. There's two basic situations that can happen. And when we get excess carriers going into a particular place or whatever, we call that injection. It just means they're kind of being forced into that area. So you can have low-level injection. That's when there's not that many more extra carriers. Or you can get high-level injection, and that is when you have a whole bunch, and we're really not going to consider that particular situation because that's basically adding so many extra carriers that the majority carriers are overrun. So we're not going to consider that. We're only going to think about low-level injection, which is really, really easy. Under low-level injection conditions, and this is where you have to pay attention because this is the part that you have to remember. If you have excess minority carriers, remember we're going to have majority and minority carriers because there already were majority and minority carriers, and we added a few more, but not enough to change the balance of minority and majority. So if electrons are the majority carrier and holes are the minority carrier, and we add a few more electrons and a few more holes, we don't add so many that electrons aren't the majority anymore. So that's basically what we mean. But the amount of time a minority carrier will live, if it's an excess, can be quantified, actually. If you take the recombination rate, first of all, and this is not a typo, the generated number of electrons and holes are the same. So that means that the number you have extra divided by how much time they're going to last is going to be a ratio that's the same. So that's why we have n of t and n of t over both, is just because that relationship works. We're still not quite where we're going to be. But what kind of function describes things that grow or decay? Exponential. And that's what happens with excess carriers. That the excess carriers basically at any time t just equals the number you started with times e to the minus t over tau. And if you have taken, or if you are taking circuits 1, and you talk about capacitors and inductors and charging and discharging, they follow an exponential, and it's usually e to the minus t over tau. In fact, e to the minus t over tau describes just about everything that grows or shrinks in the world. It also describes population growths and other types of things. So this is no different than any other type of thing that grows or decays. We can describe the function, and if we look at a situation in which we have excess carriers and we know what the initial concentration was, and we want to know, and we know what the excess carrier lifetime is, we can actually figure out how many carriers there are after however many seconds. So the value of, I can't make deltas very well when they're lowercase, but the value of this function is going to be delta NO e to the minus t over, and then we use tau of PO because we actually have that. Whoops, that's an NO. No, that's okay. That'll work. Excuse me. There we go. So the initial we had was 10 to the 15. We e to the minus t over 10 to the minus 6, which was the excess carrier lifetime. So basically, either one, it's going to be the same. So once we have a function for that, we can figure out delta n of 0 is just going to be 1 times 10 to the 15. So we can just put that there. And then if we plug in delta n of 4, we'll get 10 to the 15 e to the minus 4. And these are 4, excuse me. Is that like a 4 micro or just a 4? I don't know. But I did, yeah, it is, because we get one more. 10 to the minus 6. And we get 3.68 times. Oh, you know what? I skipped 1. I'm sorry. I'm doing 1 right now, not 4. You can tell it's Thursday. I don't like Thursdays. And we can go through each one of these numbers, and you'll notice that the value gets smaller and smaller as we go. And it decreases rather rapidly as we go. I'm almost thinking that, yeah, that's microseconds. So there we go. So this should be, we actually should have, I will just scribble this out. No, I won't. I will use my eraser because I have an eraser and I can use my eraser. I do not need to scribble. There we go. Okay. Now, what this means, just so you don't get confused later on, I still can't write today. Ugh. Okay, fine. No, let me have that. Okay, let me erase that. Okay. Let me draw again. A delta, an n, and a 1. So that would be 1 times 10 to the 15 e to the minus 1 over 1, because it's 1 times 10 to the 6, and this is in microseconds. So I just didn't want you to feel like I was pulling the wool over your eyes, and that wasn't the actual answer. So e to the minus, that would be e to the minus 4, and so forth. So one of the things that I hate is trying to think in one part of my brain while I'm talking in the other. So anyway, that's not very complicated or difficult. You just kind of have to know what happens with extra carriers. Eventually we go back to thermal equilibrium, and that's what we have. If we were to look at a graph of that exponential, that's basically what we would get. And you'll notice that the time constant was 1 microsecond, and by 5 time constants, they're pretty much gone, and that's also standard for exponential decay, that it takes about 5 time constants and you have nothing left. So that's basically what happens with excess carrier. Like I said, I'm not going to do every problem on here because a lot of them we have pretty much done. In fact, problem 1, problem 2, problem 3, problem 4, there are explanations of how to do those. So for problems, let's see, there is the information, and that is on D2L. So if you suddenly can't remember if you can bring a formula sheet or what day the test is, it's there just for your edification. And problems 1, 2, 3, and 4, we've pretty much done in class or as participation problems. But you can look at them if you can't remember how to solve them. They're there. But this is related to what we've done today. So let's say we have a sample in which the acceptor concentration is 10 to the 14 per cubic centimeter, and it is p-type material. The minority carrier lifetime is found to be 10 microseconds, and we want to know what the lifetime is of the majority carriers. So what this means is this is generation and recombination, but this is in the case where you're in a state where you've already reached equilibrium. So that's why I want to do this problem, because this is related to what we just did, but it's different than what we just did. We talked about excess carriers, but we didn't talk about carriers that are being generated and recombined in material. So what this means is that the number of acceptors is 10 to the 14, and the lifetime of the electrons, which are the minority carrier, is 10 microseconds. We know that the number of electrons divided by the lifetime of the electrons is going to equal the number of holes divided by the lifetime of the holes. That is something that is slightly different than what I was talking about. It's the same ratio, but when I was talking about excess carriers, I was saying they were being made and unmade at the same rate. This is actually thermal equilibrium material, and it's still generating and recombining, but it's going to be a little bit different. So we know from the number of acceptors and the fact that this has been completely ionized that the number of holes is going to also equal 10 to the 14, because that's the number of acceptors. And we can figure out the number of electrons by taking Ni squared over PO, and this is silicon. So this is 1.5 times 10 to the 10 squared over 10 to the 14. And we get 2.25 times 10 to the 6 per cubic centimeter. Then that means that the lifetime of the holes is going to be equal to the lifetime of the number of holes divided by the number of electrons times the carrier lifetime of the holes. That's kind of a weird looking n, sorry. So we can take 10 to the 14 and we can divide by 2.25 times 10 to the 6 and multiply by 10 microseconds. It's 444 seconds, which is still a long time. It makes much more sense. The minority carrier, they live about 10 microseconds. The majority carriers is 444 seconds, which is longer. It's over a minute. So that's a big difference, a microsecond and a minute. And sometimes you'll find that the majority carriers last days, and then the minority carriers just come and go really fast, and that's pretty common. The generation rate for electrons and holes is just found by taking the, say, number of electrons over the mean time. And if we take 2.25 times 10 to the 6 and divide by 10 times 10 to the minus 6, we get, this is where I get my 2.25 times 10 to the 11 per cubic centimeter per second, which makes much more sense. And the generation rate for electrons and holes is the same. So once you calculate one, you calculate the other. And the recombination rate is also equal to the generation rate. So we only just need to say that the recombination rate equals the generation rate, which is 2.25 times 10 to the 11 per cubic centimeter per second. So that is a problem that is related to what we just did, but in a different way. The thing to remember when you're at thermal equilibrium is that there will be electrons and holes always generating and recombining. The rate of generation and recombination is going to be the same when they're in thermal equilibrium, but they will be generating and recombining. And the minority carrier lifetime is going to be really short, and the majority carrier lifetime is going to be long, which makes sense. So if you can get that in your head, then you'll know what to expect if you happen to be doing a kind of problem.